Algebra 2, Modeling with Exponential Functions. A half-life is the amount of time it takes a substance to decay to half of its original amount. So, for question 1, we have an experimental drug that's been developed for the treatment of COVID-19. The drug, which is administered intravenously, has a half-life of 6 hours. So what this means is the drug, from whatever amount of drug you start with, or you administer, that in 6 hours, half of that amount will remain. So let's take a look at question A. It says, how much drug is left after 6 hours if the initial dose is 200 milliliters? Well, just like the name implies, half-life means half of that amount will remain after 6 hours. So we're going to put 100 milliliters for this answer. So the next question says, write an equation for the amount of drug left in a patient in terms of the number of hours since the first dose was administered if the initial dose was 200 milliliters. All right, so let's start with 200 milliliters. This is going to be an exponential function, so I'm going to multiply by some number. We'll just call this b for base. And I'm going to multiply 6 times, because that's 6 hours. I want the function in terms of the number of hours, so that exponent would need to be the 6. And then it should equal the amount 100. So now that I know this is true, I have 200 milliliters. I'm multiplying by b 6 times because there's 6 hours, and I get 100 milliliters. So to solve the equation, the first thing I can do is inverse operations. Notice the 200 is multiplied by the b to the 6th. So I will divide by the 200 and get b to the 6th equals 1/2. 100 over 200 is 1/2. Okay, the next step in the process is to get rid of this 6th power. Well, the opposite of raising a variable to the 6th power is taking a 6th root. So we'll say b is equal to the 6th root of 1/2. And so this b is my multiplier. It is what I'm multiplying times my 200. So for the equation, we could put y equals, or let's see, in this case, let's put f of x. I'll do f of x equals 200 multiplied by the multiplier 6th root of 1/2, and that's raised to the x power. Classify the function represented by the equation. Well, notice we're multiplying over and over, so we have an exponential function here. So just write exponential. Part C, graph and analyze the equation. What are the intercepts in behavior and asymptotes? So what I've done is I've gone and used my Desmos app on my tablet. You can get the Desmos app for your phone, and they look pretty much the same. So if you haven't downloaded Desmos for your phone, I highly recommend it. Let's type in the function f of x. So I'm going to press, or actually I think I'll just put y equals just to save a little time. Y equals 200 multiplied by the quantity square root of, or actually it's the 6th root of. So to get a 6th root, there's a keyboard down here at the bottom. You're going to press that and go over to functions and choose miscellaneous. And on the list is nth root. So press on that nth root and it'll pop that in for you. So let me do that again. There it is. Now I need the 6th root of 1/2. So I'm going to do 1 divided by 2. And it's going to put the 6th root of 1/2 in the parentheses. Now I'm going to go back out, close my parentheses, and then I'm going to do a to the b to make an exponent, and then I need to put the x for my exponent. So this is an exponential function. Now you're not seeing much over here, depending on how your window looks. So what I'm going to do is close this window, and then I'm going to zoom out, and then you'll be able to see it. It's way up here. Now, if I want to make this really better, what I would like to do is take my y max, and let's bring that way down, or way up, I should say. So I need my y maximum to hit at least 200. So let's put 200 here. My y minimum, you don't really have to go below the axis, but I usually go below it a little bit. So I'll do -10. Of course, you can scoot it around once you get it done. I don't really need to go to 80 on the x, so I'm thinking 48 would be 2 days, 48 hours. That's probably sufficient. We can start at 0, and I'm guessing we could call this axis x and count by 6 goes into 48, or we could do 4 or 2. I don't know. How about 6? That'll work. And then because every 6 hours is going to decay by half. Now, if I'm going from -10 to 200, I definitely don't want to count by 1. So let's do 10s. You can take off your minor grid lines. I've already done that. And then click here, and you should see a really nice graph. So you can move it here. Now, up here, if you'll tap on the point, it'll highlight that point for you. That is your y-intercept. There are no y-intercepts down here. You can run your finger along the graph, and it'll show you these values. They won't stay, though. Even if you press it twice, these don't stay, because none of these points are that significant. But you can kind of tell what the numbers are going to be, and we'll use that in just a moment. So to make your sketch, simply don't make a lot of detail here. Just a rough sketch is fine, but it should start at the 200 milliliters. So this is 200 milliliters, and this is the amount of drug in the system. So we'll just put the amount of drug over here for my label. And then the graph is dropping, and it's approaching 0. So this would be x hours. This is your time. And so that's a sufficient graph. So what are the intercepts? Well, there's only one intercept, and that's the y-intercept. The y-intercept is 200. What is the end behavior? Well, as x goes to infinity, the y goes to infinity as well. So we'll say as x approaches infinity, y approaches, not infinity, it approaches 0. And it's approaching it from the top, so I'm going to put a plus sign there. It will never reach 0, but in the real world, I guess it is possible for the drug to completely leave someone's system, so that's probably not realistic. But in mathematical terms, we know exponential functions do not cross, at least this exponential function does not cross the x-axis. All right, what about asymptotes? Well, the asymptote is actually the x-axis, so you would say the asymptote is y is equal to 0. Part D. If a patient must be administered a new dose when the amount of drug remaining reaches 50 milliliters, then when should a patient receive the second dose? Now here on the graph, just a moment ago, notice we can press on this graph and it'll show us about when it reaches 50. So over here is 50, so it's somewhere in here. But does it reach exactly 50? It might. It's hard to tell, but it's somewhere in between the, what? Maybe it's right on the 12. Well, one way to find out is to go back and let's add a table. And I know it's real close to 12 hours, or it may even be 12 hours. So I'm going to do the points right around that. So let's do plus to add a table and choose table. And then place, let's try 11, 12, and 13 for our x values. We'll just get really close to that 12. Now, I do want function notation up here because I'm going to use this. So I'm going to go back and change the name of my function to f of x. So let me take that out and change that. You'll use your little keyboard down at the bottom. You can use these variables. If you're on your phone, you kind of have to do it this way, and your tablet as well. All right, so let's put f of x. And why would we do that? Well, because over here, if I type, get rid of that, I can put f of x1. Oh, I forgot the 1. I need that. And notice what it's doing. It actually filled in these y values for me. So, and it plots them on the graph too. So these 3 points are showing me at 11 it's 56, at 12 it's exactly 50, and at 13 it's at 44. So it says if a patient must receive their new dose when the amount remaining is 50 milliliters, when should they receive it? Well, according to this, and I'll just go ahead and put the table in here, at 12 my table had an amount of 50. So let's just put that one ordered pair in the table because that's the one that matters. So in 12 hours, they need to get their new dose. Question 2. An incredibly large piece of paper has a thickness of only 0.004 inches. This piece of paper is folded in half, and the folded paper is folded in half again. And the thickness of the folded paper is a function of the number of folds. So what we have here is a table to help us organize our thoughts. We'll start with a thickness of 0.004, and these are inches. So I should probably put my units up here. These are inches. And these are our number of folds. So there's no folds, that's your thickness. Well, if you fold once, the piece of paper doubles in thickness. So this number is doubled. And so as you fold the paper, this thickness will continue to double. So to do our process, the first row of the table, we can just put our thickness of our page. There's nothing really to do here. But in the second row, we can multiply that by 2 to get the new number here. And then we can multiply this by 2 again. You may notice I'm not changing what's already here. I want to just continue maybe multiplying by another 2 each time. So this would be 0.016. And then we multiply by 2 again. Now, after you've done a few of these, hopefully you'll realize we don't really have to write all these 2's. There is a shortcut. So this is the same as 0.004 times 2 to the third power. So when I write the next row, instead of writing this 4 times, let's write it the other way. 0.004 times 2 to the fourth power. The next one would be 0.04 times 2 to the fifth power. And if you'll pay attention over here on the left side, these numbers that you see are equal to these exponents. Here we would have an exponent of 3. Here we would have an exponent of 2. Here we would have an exponent of 1. And since there's no 2's, that's like 2 to the 0 power. So using that, we can write an expression for the nth fold. That would be 0.004 times 2 to the nth power. So that's the expression in your last row. B says to write an equation for the thickness of the paper as a function of the number of folds. So the notation here says T of N, so I guess that stands for thickness, after N folds, because this is N folds, and that will equal this expression you've already written in the last row of your table. So that's 0.004 times 2 to the nth power. How thick is the paper after 10 folds? To find the answer, we simply evaluate our function when n is 10. So if you plug in a 10, you will multiply 0.004 by 2 10 times, and you will get 4.096 inches. So that is the thickness of the stack after 10 folds. Part D. How many folds will it take for the thickness of the stack to be as tall as the Pascagoula Lighthouse, which is 50 feet tall? To do this, we need to convert 50 feet into inches. So one way to do that is to use that conversion factor, 1 foot is equal to 12 inches. So to convert feet into inches, we will multiply 50 feet over 1 times 12 inches over 1 foot. And the purpose is basically to divide out our units feet and convert to inches. So multiplying 50 times 12, we will get 600 inches. So here's the lighthouse is basically 600 feet tall. So I've typed in, I've got a bunch of stuff typed in here. Let me get rid of this. What I really need is to type in y is equal to 600 to add a horizontal line to this graph. Now you can't see 600 because it's way up there. So I'm going to close this and I'm going to zoom way out. And you can just keep zooming until you get to it. It's way up here. And I'm not going to spend a lot of time on this graph because really all I have to do is tap right here to see the number. Now the number I'm getting is a decimal, 17.195, but you can't really have a decimal for a number of folds. Folds would be integers. So would I need 17 folds? Well, if I do 17 folds, I won't be at the 600. I'll be just below it. If I do 18 folds, I'll exceed 600. So for the answer to question D, we're going to need 18 folds because 18 folds would actually go past the 50 feet that we want. How many folds will it take for the thickness of the stack to reach from the Earth to the Moon? That is 238,900 miles. Well, once again, we are in another unit other than inches. So we will convert 238,900 miles into inches. To do this conversion, we'll start with 238,900 miles, and we will multiply by the fraction 5,280 feet over 1 mile. That's because 1 mile is 5,280 feet. Doing that will basically eliminate your miles. We don't want feet, however, so we'll do this again. We're going to convert feet to inches. Well, 1 foot is equivalent to 12 inches, so put 12 inches over 1 foot, and that will divide out your feet. So these three numbers multiplied together will be the distance from here to the Moon in inches. Now to find this number, I've typed in y is equal to those three numbers multiplied out. It does convert this into scientific notation, but that's not that important. The most important thing is going to be my x-coordinate, so I will never really need this number as part of my answer. Now to get this answer, I had to really go far out here, and let me show you how to do it. Just go to your y and type in the numbers multiplied. So the first one was 2, 3, oops, let me back up there, 2, 3, 8, 9, 0, 0, times 5,280 times 12. And it'll convert that into exponential automatically because the numbers are so huge. So you see that it's done that. So now I want to know when this reaches that. So notice it's a horizontal line up here. So let's tap on this point of intersection and it will give you the coordinate where the two graphs meet. Now notice the x-coordinate is 41.783. Again, we can't have a decimal answer. So that's telling us we'll need 42 folds to get to the Moon. So the answer to question E is just 42 folds. And question E, finally, how many folds will it take for the stack of paper, or the thickness of that stack, to reach from here to the sun? That's 93 million miles. So most of the time when I ask a student a question like this, they think it's going to take millions of folds. But you'll be surprised. It doesn't take that many folds. So we're going to go ahead and convert 93 million miles into inches doing the same strategy. So to do this conversion, we'll multiply 93 million miles over 1 times 5,280 feet over 1 mile. And this will divide out your miles. Then we'll multiply by 12 inches over 1 foot. This will divide out your feet. So now we have the distance from here to the sun in inches. So once again, I've typed in y equals, and this time I put 93 million times 5,280, and you'll have to scoot over here to see this, and then I multiplied by 12, and it came out with this huge number. To see it on your graph, you'll need to take your y max and actually type that in again. So 93 million times 5,280 times 12, and then it'll convert the step for you to make it work, because this is huge. So notice I've adjusted my x's. That really isn't necessary. The thing I want to do is find this point. So I'm going to click on that. And so you will notice it's only going to take 51 folds. 51 folds for the thickness of this stack to reach the sun. So the answer to the last question is 51 folds. Now you may be saying to yourself, okay, I only have to fold a piece of paper 51 times for it to reach to the sun. And yes, actually, that's true, but it is not possible to fold a piece of paper 51 times. In fact, I would encourage you, just for the fun of it, take a piece of paper in your house and fold it and see how many times you can fold it. If you will give me that answer with this assignment, I'll attach an extra bonus to your assignment for this grade. So check it out. It's not very many folds. But this is kind of a surprising answer to this question. Students usually go, what? So to recap, today we looked at basically two functions. The first function was exponential decay, and that was the function where the patient was taking a dose of medication for the coronavirus. And the second equation that we developed was an exponential growth equation. And we examined that growth by using the equation in our Desmos graphing calculator. Keep working hard. I will see you guys later.